So we're in the end of topic test for 313 probability concepts, and question 2. Okay, question 2 looks like we've got competition, spin the wheel, and whatever number is, you get that taken off the price of your car. The normally costs $40. Okay, so there's some sectors here with $10, some at 20, some at 30, some are entirely free. And over the week we've recorded the number of customers get each prize in that graph, and we're actually told that 270 of the 500 customers got the 10. How does this line up with what happened in theory? Okay, so I've got to come up with some sort of theoretical model. My theoretical model will be that each of these sectors is equally likely to occur, and from that I can work out the probability of getting a $10 discount, and I'll be comparing that with what we actually got. So theory, each sector equally likely, and from that theoretical model, it implies that the probability of a $10 discount equals, so how many are 10? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 8 out of 16, which is 0.5. And from my experimental, well, in the experiment and what actually happened during the week, the probability of a $10 discount equals 270 over 500, which is 0.54. How does this line up with expected in theory? Okay, so the experimental probability is higher than theory would suggest. But we don't expect to get exactly that. There's going to be some variation week on week, even if that was the true probability of 0.5. But some variation week on week, i.e. in each sample. So if the true probability was 0.5, we'd expect it in the long run to average out at 0.5, but 0.54, is that really that different? There are tests we can do in probability distributions to look at that. Okay, now in part 2, describe how these two probabilities compare with the true probability. Well, the true probability is unknown. Okay, will be influenced by the wheel itself. The wheel, e.g., is wheel equally balanced or biased? Is wheel spun from same start point each time? That in itself could have an influence on it. And is strength of spin a factor? I think it would be. It would be. So the true probability is unknown. The long run experimental probability should approach the true probability. If the wheel is unbiased, and we choose a random start point, and the strength of the spin is not a factor, and spin OK, then theoretical probability is good approximation to the true probability. Okay, let's have a look now at part B. Did a survey of the customers. Said they were really happy with the survey, so that's good. Really happy with the stuff they've received. What else have we got? So 90%, sorry, I was just distracted there. Happy. 8% were cut by Terence. 3% that were not served by Terence and not happy. Okay, so let's form a little bit of a two-way table. So happy, not happy, Terence, not Terence. 90% said they were happy. 8% customers had their hair cut by Terence. 3% that said they were not served by Terence, and they were not happy, so that's 3%. Okay, well, happy and not happy have got to add up to 100%, so that must be 10%. And Terence and not Terence must add up to 100%, so that there must be 92%. So 89%, oh, 1%, and 7%. Let's just check that. 1, 7's 8, 89 and 3 is 92, that's 100, that's 100, that's 100. So are they mutually exclusive? Mutually exclusive if the probability of Terence and happy equals 0. Well, the probability of Terence and happy is 1% here. Probably Terence and happy, Terence and happy is 1%, which is not equal to 0, therefore not mutually exclusive. Nice. Now, should Terence's boss be concerned by the results of the survey? So let's see. Probably if I'm going to see how well Terence satisfies the customers. If Terence satisfies the customers equally well to the people, to the other hairdressers, then he shouldn't be concerned. If there's a difference, there might be a reason for concern. So I want to find the probability of happy given served by Terence. Okay, so we're just looking at served by Terence. So that's 1 out of 8, 0.125, and the probability of happy if not served by Terence, well, that's 89 out of 92, which seems to be a lot higher. Just grab that on my calculator. It's a lot higher, isn't it? 89 divided by 92, 0.9674. So in terms of a relative risk, so the probability of happy, so not by Terence, served by Terence, divided by the probability of happy served by Terence, that's 0.9674 over 0.125, which is 125, holy moly, 7.739, i.e. customers are 7.74 times more likely to be happy with the service if they're served by another hairdresser than if they're served by Terence. So the boss should be concerned. Okay, so we've looked at the two conditional probabilities, happy served by Terence and happy not served by Terence, and we've found that if you're happy and you're not served by Terence, that's much more likely than being happy if you're served by Terence. So that's a reason for concern for the boss. Okay, I'll find the mark schedule and we'll mark this one.